Hey everybody, Trey here. Welcome back to another video. Today we're going to go well back into the archives and dive into one of the more prolific tornado outbreaks ever in the central and southern plains, and that is the April 26, 1991 outbreak centered on Kansas and Oklahoma. 55 tornadoes occurred as part of this event, 12 of which were rated F3 or higher, including the destructive Andover, Kansas F5 you see here, which tore a 45-mile-long path through the suburbs of Wichita. I'm sure many of you are familiar with this footage of the tornado as it passed through McConnell Air Force Base on the southeast side of Wichita. This footage has been used in countless tornado films and documentaries and is some of the most iconic tornado footage of all time. There was also the Red Rock, Oklahoma F4, in which mobile radar measured winds in excess of 265 miles per hour along its 66-mile path, and the infamous Kansas Turnpike tornado, during which a Wichita news crew took quote-unquote shelter with a family underneath an overpass as the tornado bore down on them. This is certainly one of the more famous, well-documented events in recent memory, and I know it was an event that spurred a lot of folks to pursue their interest in meteorology, including myself. When I was little, I wore out my VHS copy of the National Geographic documentary called Cyclone, which talked about tornadoes and hurricanes and actually focused on the April 26, 1991 event during its tornado segment. Its penchant for producing strong to violent tornadoes has seldom been matched since in the central and southern plains, so we're going to take a deep dive into the meteorology behind this event and show you why this was such a prolific tornado outbreak. Just a quick note before we dive in, many of you have asked me to do historical case studies from 30, 40, 50 plus years ago, including this event, and the issue with these old case studies is that most data archives, including the ones I typically use, don't go back that far in time, or if they do, the data is incomplete. Also, the technology back then was nowhere near what it is today, so the data we do have is often much lower quality, and as a result, it's tough to go into detail on things like storm behaviors and such. So these older events are much more challenging to cover. However, we do have enough data to discuss the meteorology behind this event in depth. I'll be using sites like the Tornado Archive and the Violent Tornado webpage from the SPC. Now keep in mind that both of these sites use reanalysis data, meaning that the upper air data and other products, such as CAPE and SHEAR, are essentially estimates instead of observed data. But they are really good estimates and give us a coherent data set that we can use to analyze the environment on April 26, 1991. Other data, such as radar and satellite, are a little tougher to find. I'll go into this a bit later. So this case study may be a bit more piecemeal than normal, as I had to pull things from a bunch of different sources, but we should still be able to put together a detailed analysis of the science behind this outbreak. Also, a quick reminder about my Patreon page. If you're interested in supporting the Convective Chronicles channel and receiving some extra perks, including exclusive videos, sneak peeks at upcoming content, and access to my AI-powered chatbot called Treybot, head on over to Patreon and become a patron today. So without further ado, let's go ahead and get started. The April 26, 1991 event was very well forecast. Back then, the Storm Prediction Center was called the National Severe Storms Forecast Center, or NSSFC, and by their Day 2 outlook they had included mention of, quote, the potential for a significant tornado outbreak in the central United States on Friday, April 26th. They upgraded to high risk by their initial Day 1 outlook, as you see here. At this time, risk categories only included general thunderstorm, slight, and high, so a setup that would receive a moderate risk today might fall under the high risk category back then, but as you'll see as we go through the meteorology of this event, it certainly deserved a high risk designation regardless of the era. The high-risk area would shift slightly northward and expand throughout the day, covering much of the central plains from northern Nebraska through the eastern half of Kansas into Oklahoma. This outbreak spawned 55 tornadoes from northeast Texas all the way to Iowa, most concentrated from northern Oklahoma into Kansas, where many were long-tracked and significant. Tornadoes were directly responsible for 21 deaths in all, 17 of which came from the Andover, Kansas F5 alone. We also had over 200 large hail reports spanning the plains into the Midwest, contributing to a total of over 330 severe weather reports for the entirety of the event. Alright, let's dive into the meteorology behind this event. We'll start by using data from the Tornado Archive. I'll put a link to their site in the description box below. We'll begin at 500 millibars at 12Z, 7 a.m. Central Time on April 26th. Again, this is reanalysis data, so it's technically an estimate, but it is a pretty close approximation of what the atmosphere looked like on this day. Right away, your eyes are drawn to this massive, high-amplitude trough encompassing pretty much the entire western half of the U.S. If we were to draw in the trough axis, it would look something like this. Very impressive negative tilt to this trough. We've talked about the differences between positive and negatively tilted troughs ad nauseum on the channel before. Negatively tilted troughs tend to be closer to maturity, and a more mature, stronger trough in the mid and upper levels means a stronger cyclone in the low levels. As a result, your low-level and deep layer wind shear tends to be stronger, and you often see greater differential temperature advection in the vertical, more intense warm air advection in the low levels, and stronger cold air advection aloft, often increasing instability. Now, as we've talked about before, you can still get severe weather with positively tilted troughs, but a large percentage of your more significant tornado outbreaks are associated with more negatively tilted troughs, and the one on April 26, 1991 was pretty textbook. It would gradually eject into the central plains throughout the day, timed perfectly with the peak in solar heating during the afternoon. One of the reasons why a stronger, more negatively tilted upper-level trough yields a stronger low-level cyclone is that negatively tilted troughs tend to be associated with more divergence aloft, which corresponds to more convergence at the surface, and more surface convergence produces more intense surface low development. Defluence, as we often talk about on this channel, is basically the directional portion of the divergence equation. It's the spreading apart of those wind vectors in the upper levels of the atmosphere which creates a void. And to fill that void, air is brought upward from below, and that's how you get large-scale rising motion that can prime the atmosphere for storm initiation in a given environment. We can diagnose defluence at the 300 millibar level, and for that we'll use the SPC's Violent Tornado webpage, since the Tornado Archive does not include 300 millibar data. The brown lines are the geopotential height contours, and the wind barbs are colored in light blue. And as we progress through the day, we see impressive defluence develop in the exit region of the trough over a very broad region, basically from South Dakota and Nebraska, where winds are much more out of the south, down to Kansas and Oklahoma, where winds have a much more westerly component. This was in part why we had such a large area of elevated severe weather risk on April 26th. You had synoptic scale forcing for ascent over a very large expanse of the plains, which would help condition the environment for storm initiation where the other ingredients for supercells were in place. Heading down to the surface, we had already begun to see surface cyclogenesis over a large area on the lee side of the Rockies by the start of the day on the 26th. We'd seen that broad southwesterly flow associated with the incoming upper trough start to overspread the Rockies the previous day. Here's the 500 millibar chart at 7 a.m. Central Time on April 25th, the day before the event, taken from the NOAA Daily Weather Maps publication for the week of April 22nd through 28th. And you can see our trough starting to make its way into the western U.S., with that belt of stronger flow approaching the Rockies. And with some eastward progress through the day on the 25th, we started to initiate that lee cyclogenesis process. So by the morning of the 26th, we had a broad surface low in place from southern Canada all the way into the southern plains. We'd also begun to see moisture advection in earnest across the central and southern plains. Mid-60s dew points, denoted by the darker blue colors, were already up into central Kansas by morning. Going back to our surface data from the previous morning, we see those 60s and 70s dew points were already sitting in central Texas, so it wasn't going to take much to get those into the central plains, and with strong low-level cyclogenesis underway, they had no issues moving northward. And they would continue to advect northward throughout the day, with 60s dew points all the way into eastern Nebraska by late afternoon. Zooming in on our data at 22Z, there also appears to be a bit of a dryline bulge that developed here in far northern Oklahoma. Notice how the dryline kind of bows outward in this area. This is a dryline bulge. These occur when localized surges of stronger tropospheric flow allow segments of the dryline to advance or bulge forward. Low-level convergence and wind shear are maximized at these dryline bulges, so they're often a favored location for severe storm formation when all else is equal. Typically, you'd want to target just east or northeast of the dryline bulge, and in this case, that appears to be right in northern Oklahoma into southern Kansas. Now again, this is estimated data, so let's take a look at our raw surface data to see if this was indeed the case. Unfortunately, I was unable to obtain surface observations at every single hour from the morning through the evening like we usually analyze, but we do have a few sets of observations that will help us piece things together. This is the surface data at 12Z, again taken from the NOAA Daily Weather Maps publication. 69 over 67 at Oklahoma City, 66 over 64 at Wichita, so that moisture was quickly making its way northward. Moving on to 18Z, 1 p.m. Central Time, we start to see that dry line tighten up and become more evident across Kansas and Oklahoma. Dew points in the 60s across the eastern half of Kansas into much of Oklahoma, with much drier air to the west. Dew points in the 20s, 30s, and 40s out here across western Oklahoma, western Kansas, into the Texas Panhandle. So if we were to draw in our dry line, it would look something like this. Perhaps bowing outward here in southern Kansas, then drifting back to the southwest across western Oklahoma, before becoming a bit more north-south across northwest Texas. So there certainly does appear to be a dryline bulge situated across northern Oklahoma into southern Kansas. If I was storm chasing on this day, just looking at this surface map, I'd want to set up in that area straddling the Kansas-Oklahoma border right ahead of the dryline bulge. Perhaps a bit stronger surface convergence here, making it a preferred area for storm initiation, even though we did have ample convergence along the entirety of the dry line. southwesterly flow on the dry side, nicely backed southerly or southeasterly flow on the moist side. Fast forward to 21Z, 4 p.m. Central Time, and the orientation of the dry line hadn't changed much. Very juicy air mass ahead of the dry line, 80 over 67 at Wichita, 81 over 69 at Ponca City. By this time, convective initiation was well underway, especially from east central into northeast Kansas and southeast Nebraska. Multiple tornadoes had already occurred or were ongoing across this portion of the risk area, including an F3 that was in progress at this time and tracked from Washington, Kansas to near Beatrice, Nebraska. By 22Z, storm initiation was underway across northern Oklahoma and southern Kansas. You can see the thunderstorm symbol on the observation at Enid. Out of this convection would come the Red Rock and Andover tornadic supercells. In addition, there may have been an outflow boundary in play across southeast Kansas. Now again, we don't have radar and satellite data in full throughout the day to corroborate this, but we can piece together some evidence from other sources. Take a look at this special weather statement from the NWS office in Wichita early on April 26th. They note that severe thunderstorms were located between the Kansas-Oklahoma border and Enid at 5 a.m., moving northeast at 35 miles an hour. Severe thunderstorm watches were also outlined across northern Oklahoma into southeast Kansas through about midday, and a couple of F2 tornadoes occurred in these areas during the morning, one near Tonkawa in far northern Oklahoma, and one in Montgomery County, Kansas. So it's fair to assume that we had a pretty potent complex of storms with this early round, and we can also infer that this batch of storms likely left some rain-cooled outflow in its wake. Let's go back to our 18Z surface map here, and we can clearly identify a temperature gradient and wind shift across southeast Kansas. Temperatures in the mid to upper 60s across southeast Kansas, upper 70s to near 80 across northern Oklahoma. We also have a bit more backed southeasterly flow on the cool side of the boundary, a more southerly component on the warm side. So there was definitely a well-defined outflow boundary draped across southeast Kansas heading into the afternoon. By 21Z, it had become much more diffuse, likely due to solar heating on both sides of the boundary. We can still see some remnants of it, likely right in here. These more diffuse outflow boundaries are often much more conducive for tornadic activity along them. You never really want a sharply defined boundary or one that's surging quickly, as those will tend to either force a bunch of convection along them or limit the amount of time storms can spend along the boundary. Now the question is whether or not this actually played a role in the afternoon round of storms. The environment was already quite favorable for tornadic supercells, so we didn't need the boundary, and it does appear to be a tad removed from the most robust supercells in this area. Andover is right in here, obviously Red Rock much farther to the south. But it certainly is an interesting feature that was at least in the vicinity of the afternoon and evening round of supercells. Back up to 850 millibars, we see a broad plume of strong low-level flow associated with the low-level jet. Again, we had that broad low-level cyclone that was continuing to develop across much of the plains, and that allowed low-level flow to strengthen out ahead of it. 50 knots or so of flow across Kansas and Oklahoma to start the day. It would wane a little bit through the morning into the afternoon, but we would maintain at least a moderate low-level jet across the region for the entirety of the day. 40 knots or so of flow by the time the afternoon round of storms began to initiate along the dry line, and an even further increase near and after sunset. So you can see, without even looking at a sounding, that we had a very favorable wind profile for supercells. 10 to 20 knots of surface flow out of the south-southeast, veering and strengthening to about 40 to 50 knots of 850 millibar flow out of the south-southwest, beneath about 50 to 70 knots of 500 millibar flow out of the southwest. A pretty classic wind profile for tornadic supercells. Now let's take a look at a few soundings from across the region to really get a sense of the environment. We're going to look at a couple of observed soundings at 12Z and 0Z, so 7 a.m. and 7 p.m. Central Time, from both Norman, Oklahoma and Topeka, Kansas. We'll start out at Norman at 12Z, and this is a pretty textbook sounding for the morning of a significant severe weather event. For starters, we already have a very deep low-level moist layer extending up to about 750 millibars. You can see the red line, which is our atmospheric temperature profile, and our green line, which is the atmospheric dew point profile, are very close together up to about 750 millibars, which indicates that the quality of low-level moisture is very high. Tornadic supercells love a deep moist layer as it gives them a lot of juice and energy to feed off of, and in this case that moist layer was expected to deepen even further throughout the day, given strong low-level warm moist advection. This moist layer was situated beneath a deep elevated mixed layer, or EML, denoted by this thick layer of very steep lapse rates in the mid-levels. As we often discuss on this channel, the EML is that layer of warm, dry, well-mixed air that emanates from the higher terrain out west and gets transported atop the low-level moist layer out east amid the westerly or southwesterly mid-level flow. This helps thwart thunderstorm development for much of the day until the cap erodes and allows instability to build effectively. We did have those morning storms from northern Oklahoma into southern Kansas, so there must have been enough forcing and likely mostly elevated instability across this area to support storm formation. About 2,500 joules per kilogram mixed layer CAPE here at Norman. But we didn't see redevelopment behind this early round until mid-afternoon, so the EML likely did its job and allowed the atmosphere to fully recover. All in all, this was your classic loaded gun sounding, indicative of an explosive environment ready to go to work once the cap fully eroded. At 12Z at Topeka, we were north of the best moisture at this point, only a 52-degree dew point at the surface compared to 66 at Norman, and the EML was far more stout up here, so we would need to await the robust moisture return and the forcing from the incoming trough to help lift and cool that capping inversion to allow storm initiation to take place, and that's exactly what happened. Here is the 0Z Topeka sounding, basically at the height of the event, as the Red Rock tornado was ongoing and about an hour after the Andover tornado began, and what a difference 12 hours makes. Fully destabilized, that capping inversion had been dramatically cooled and lifted, leading to about 2,000 joules per kilogram mixed layer CAPE, greater with southern extent where the better low-level moisture was. And take a look at that moist layer. It had deepened even further and now extended above 700 millibars, yielding an extremely juicy low-level air mass for these supercells to work with. And how about that hodograph? That is a pretty classic-looking wind profile for significant tornadic supercells. Massive clockwise curvature in the low levels of the hodograph, suggestive of very strong low-level wind shear. Significant veering and strengthening of the low-level winds with height, going from 15 knots out of the southeast at the surface to about 50 knots out of the south at about a kilometer off the surface. So impressive speed and directional shear in the low levels, just shy of 500 meters squared per second squared effective storm relative helicity. Couple that with robust instability, and that is certainly an environment supportive of strong to violent tornadoes, given a favorable storm mode, which we'll talk about in just a second. Strong deep layer shear as well, very lengthy hodographs, about 80 knots of effective bulk shear, certainly favorable for organized convection. Let's dig a bit more deeply into the hodograph to explain some of the characteristics of these supercells. We'll start off by discussing the strong storm relative inflow. To determine the storm relative inflow, we draw a vector from our storm motion to the low levels of the hodograph, generally below 1 kilometer. Storm relative inflow modulates the amount of mass being taken in by a storm. The greater your storm relative inflow, the more mass the storm is ingesting, and therefore the larger your storm tends to be. Generally, 0 to 1 kilometer storm relative inflow greater than 35 knots yields larger supercells, and in this case, our storm relative inflow does appear to be just in excess of that 35 knot threshold, meaning that the supercells on April 26th were a bit on the larger side. We'll dive into some radar data a bit later, but for example, the Red Rock supercell spanned about 30 miles from its hook echo to the northern edge of the forward flank precipitation, a pretty large storm. Mid and upper level storm relative outflow was also on the large side. To find storm relative outflow, we draw a vector from the storm motion to the upper portion of the hodograph, generally above 6 kilometers. Storm relative outflow modulates how precipitation is vented away from the updraft base. Stronger storm relative outflow, generally above 40 knots, leads to efficient venting of precipitation away from a supercell's mesocyclone, yielding much more visible tornadoes. Storm relative outflow from about 6 to 7 kilometers above ground level was certainly in excess of 40 knots. There's 10, 20, 30, 40. We do see the hodograph fold back on itself a little bit in the upper levels, but we do have at least a decent layer of strong upper level storm relative outflow. We also have a bit of mid-level backing of the winds, which also helps to shunt precipitation away from the mesocyclone region of a supercell. These were some of the reasons why these tornadoes were quite visible and easy for chasers to interact with. We also have ample low-level streamwise vorticity. Streamwise vorticity, as we've discussed before, is when the storm relative wind vector, drawn from the storm motion to the level of interest on the hodograph, is more parallel to the horizontal vorticity vector, which is always perpendicular and to the left of the hodograph. When ample low-level streamwise vorticity is present, all a supercell has to do is tilt and stretch that into the vertical, and it can more easily initiate the tornado genesis process, unlike crosswise vorticity, which is when these two vectors are more perpendicular to one another. And you can see that we have a pretty good amount of streamwise vorticity in the low levels up through the lowest couple kilometers of the atmosphere. Overall, this is a pretty classic springtime profile for prolific tornado events in Oklahoma and Kansas, with strong low-level shear with ample streamwise vorticity, and strong mid-level shear with ample crosswise vorticity. Here is the 0Z Norman sounding, and we see an equally favorable environment. Explosive instability with mixed layer CAPE in excess of 4,000 joules per kilogram, and 0 to 3 kilometer CAPE in excess of 200 joules per kilogram. So stronger instability with southern extent, closer to the better low-level moisture and slightly warmer surface temperatures, favorable for very robust updrafts. Low-level shear not quite as eye-popping this far south, perhaps due to being a bit farther removed from the core of the low-level jet farther north, 1 kilometer winds at Topeka were about 50 knots, only about 30 knots at Norman, but we were still well within the range for significant tornadoes. Plenty of curvature and streamwise vorticity in the low levels of the hodograph, veering and strengthening winds with height, and still nearly 400 meters squared per second squared effective storm relative helicity, and what small quote-unquote deficit we had in low-level shear between here and areas farther north in Kansas was more than made up for by stronger instability. So all in all, this was a pretty textbook significant tornado environment. Potent, slow-moving, negative tilt upper trough, ample moisture ahead of a tight dry line, strongly veering and strengthening winds with height, and explosive instability. So as long as we could get discrete supercells out of this environment, there was a high probability that they would produce strong to violent tornadoes. Let's diagnose that storm mode. If you recall, our preconvective dry line looked something like this, mostly north-south with that bulge in the middle. If we were to compare that to the orientation of our deep layer shear vectors, we'll use our 0 to 6 kilometer shear vectors that you see here, we'd have a great deal of perpendicularity between the dry line and those shear vectors, favoring a discrete supercell mode. This is really the perfect angle between the initiating boundary and the shear vectors to get purely discrete supercells, as of course, the smaller the angle between the two, the greater the tendency for messier modes. And while a purely perpendicular or 90-degree angle between the two does initially support discrete convection, you tend to get some degradation of that favorable discrete mode thanks to a higher tendency for cell interactions to occur as the initial cells split. This may be slightly counterintuitive, but let's look at a diagram to see why this is the case. Here are a couple of examples of a purely north-south initiating boundary, denoted by the brown line, with different deep layer shear vectors you see at the top of the image. The example on the left is similar to the April 26, 1991 case, where we have a large but less than 90-degree angle between the initiating boundary and the shear vector. The example on the right is where we have a perfect 90-degree angle between the two. We're not going to go over the case where we have a small angle between the two because, as you know, that favors ample storm interaction and a tendency for upscale growth into a more linear mode. Our initial cells that form on the initiating boundary are denoted by the black circles, and the different storm splits that tend to evolve in the early portion of the storm life cycle, the left split, which moves to the left of the mean flow, and the right split, which dominates in veering wind profiles with height and moves to the right of the mean flow, are denoted by the pink and red circles respectively. In the case on the left, with a large but slightly acute angle between the initiating boundary and the shear vector, the left and right movers remain somewhat staggered with limited interaction between each cell. However, in the case on the right, while the cells start out discrete, the left and right movers are no longer staggered. In other words, the left movers have a greater chance of interacting with the right movers from other cells, which can make the storm mode a bit messier. So even though you might think that a very large angle near 90 degrees is best for discrete supercells, that's not exactly the case. Instead, a large but still slightly acute angle, probably somewhere around 70 to 75 degrees or so, will both maximize the discreteness of the initial cells along the initiating boundary and also limit interactions between the left and right movers to maintain that discrete mode for much longer. In addition, the overall forcing within the environment, both on the synoptic and mesoscale from our slow-moving trough and dry line respectively, were not overly strong, which overwhelmingly supports a discrete mode as well. Alright, let's dive into some radar data. Now, radar back in 1991 was in a bit of a transition phase. The National Weather Service was undergoing a modernization, and part of that was introducing a national network of upgraded WSR-88D radars, which are the radars we use today, replacing the old WSR-57 radars, which were becoming outdated and did not have Doppler capabilities. Unfortunately, the WSR-88D at Norman, Oklahoma was the only one of the new radars that was up and running at the time of this outbreak, and it had not yet been approved for operational use. However, the relevant Weather Service offices did utilize the Norman radar during this event and were able to drastically improve tornado warning lead times with the new higher resolution data. This event showed just how beneficial the new WSR-88D radars would be. However, this means we only have data from the Norman radar to analyze, meaning that many of the storms in this outbreak were much too far from the radar to perform any meaningful analysis. In other words, we have no low-level scans of many of these storms, especially those in Kansas, including the Andover supercell. So we won't be able to go as deeply into the radar data as we normally would, but we'll still discuss as many interesting features as we can. So here's our data from the Norman radar, KTLX, which is located here. Wichita and Andover are located here. This dataset starts at 4 p.m. on April 26th, and each successive frame is about 17 minutes apart. Obviously not the temporal and spatial resolution that we'd like to have, but at least we have some radar data to analyze. Storm initiation was well underway at this point, with multiple discrete supercells developing ahead of the dryline bulge from northern Oklahoma into southern Kansas. The first interesting thing you'll notice is the degree of storm mergers that led to the intensification of supercells. Take a look at this dominant supercell in far southern Kansas. We get additional development to its southwest that eventually appears to merge with the ongoing supercell, and once the merger was complete around 5:20 p.m., the conglomerated supercell produced its first tornado, an F0 near Anthony, Kansas, and would subsequently produce several others, including the Andover F5, which began at 5:49 p.m. and lasted for nearly an hour and a half. Even at this distance from the radar, you can see the flying eagle shape of the supercell as it was very near the Wichita Metro, producing the F5. And just a side note, this is what the WSR-57 radar at Wichita was showing at the same time. The Andover storm was being blocked by ground clutter, and we obviously can't denote anything interesting from any of these storms. So you can see what meteorologists were up against with the old radar and why the new WSR-88D network was so critical. Even at a distance of 150 miles from the Norman radar, you could tell far more about the Andover supercell with the WSR-88D than you could with the WSR-57. Another interesting merger happened with the storms in northern Oklahoma. Notice how two distinct supercells develop in close proximity to one another, producing a couple of damaging but brief tornadoes. They then merge into one dominant supercell, and around 6:30 p.m., once the merger was complete, it gave birth to the Red Rock F4, which remained in progress for nearly an hour and a half. So it looks pretty likely that storm mergers played a role in the intensification of some of the more notable supercells of the event, notably the Andover and Red Rock supercells, and may have spurred on significant tornadogenesis. Let's zoom in on the Red Rock storm at 6:33 p.m. Here we have 4 different elevation angles of the supercell at this time. The lowest level scan, 0.5 degrees on the top left, 1.5 degrees on the top right, 2.4 degrees on the bottom left, and 4.3 degrees on the bottom right. Note the textbook hook echo on this storm, classic flying eagle shape with a well-developed hook echo on its southwest flank, almost a picture-perfect radar presentation of a discrete supercell. This makes sense based on our observed photograph in which we denoted pretty solid precipitation venting away from the mesocyclone to the northeast. Also note this small region of low reflectivity surrounded by much higher reflectivity at the 2.4 degree elevation angle, in essence sort of a donut hole. This is a bounded weak echo region, indicative of a very strong updraft able to loft hydrometeors to the very upper reaches of the storm. This is corroborated by this storm's intense overshooting top evident on visible satellite. As we move on to the velocity data, very strong tornado vortex signature in the low levels extending all the way up through the storm, indicating a similarly strong mesocyclone. This was something that the old WSR-57 radars could not do, so this was pretty eye-opening data back then, and it aided in increasing warning lead times in this event. In addition, Howie Bluestein and his crew from the University of Oklahoma positioned their mobile Doppler radar about a mile from the Red Rock tornado as it crossed the road in front of them. This is their footage. In Bluestein et al. 1993, they detailed their impressive findings of 120 to 125 meter per second winds at the top of the tornado's funnel, which corresponds to 270 to 280 miles per hour. At the time, these were the first direct measurements of F5 wind speeds in a tornado. I'll put a link to their paper in the description box below. The storm to the north of the Red Rock supercell also produced a violent F4 tornado, perhaps one of the more forgotten ones of the outbreak near Winfield, Kansas. Here's some incredibly impressive footage of this tornado. Reportedly, it may have produced F5 damage, with one home so badly destroyed that NWS survey crews at first failed to notice it. An additional supercell developed to the south of the Red Rock storm along the dry line. This storm would produce multiple EF4s close to Tulsa, the first of which tore across southern Osage County near Skiatook, and the second of which was short-lived but violent and produced damage in the town of Oologah. Here's some data as the Skiatook F4 was ongoing. Each panel represents the same elevation angles as in the data for the Red Rock supercell. Once again, classic supercell radar presentation with a well-developed hook echo and precipitation vented off to the northeast. Here is the velocity data associated with this storm. Here's some data during the Oologah F4. You can see that we're at the very edge of the data domain, so it's getting even tougher to identify anything of note, but you can see the wrapped-up nature of this storm with the hook echo on its southern flank. Notice the minimal reflectivity echoes at the 4.3 degree elevation angle, which means we're basically scanning the very, very top of the storm. Pretty intense velocity couplet associated with this tornado and mesocyclone as well. So that's going to do it for this video. Hopefully you learned a few things about why this was such a prolific outbreak. I'd love to have some more modern-day radar data from tornadoes like the Andover F5, but that's just not the case. Unfortunately, we just can't go as deeply into these older events as we can with the more recent ones, but at least we can get an idea of the meteorology behind these older events to determine why they were so prolific. April 26, 1991 was a pretty textbook significant tornado setup, and those discrete supercells certainly took advantage and produced some spectacular but deadly tornadoes. With that, thanks for watching, and we'll see you in the next video.